Hello everyone, and welcome to this session on Advanced Lab Design with STAAD.Pro. I am Surajit Ghosh. Today, I'll start with a basic discussion on various modeling methods for slab, advantage and disadvantage of each method, and selection of modeling method based on the type of slab. Any concrete building consists of several structural and non-structural elements. Structural elements like beam, column or shear wall carry and transfer the gravity and lateral load to the support by forming proper load path, which depends on the nature of load. These load-bearing elements are important for the stability of the structure. After design, we finalize a section and reinforcement which can withstand applied external load without failure. Non-structural element like partition wall or internal brick wall doesn't contribute to the overall stability. So, during structural analysis, we model only those important load-bearing elements and ignore any non-structural or architectural element. When we create a structural model in STAAD for analysis and design, normally we model the beam and column center line with a member and shear wall with plate element. Then assign different sections with concrete grade and thickness of wall, apply gravity and lateral loads from different orthogonal direction, generate combinations based on relevant design code like IS 456 or ASC 7, perform analysis and based on analysis result, member force or plate stress value, design these elements in STAAD Advanced Concrete Design or RCDC module. This is a common approach for any concrete building design, but it is not entirely correct. This structural model is incomplete, as we have ignored a very important element during analysis which can change the overall design result. Concrete slab present at each floor level. When a gravity load is applied on the floor, concrete slab transfers this load to the supporting beam and column. Stiffness of the slab doesn't contribute much except reducing the out-of-plane deformation. Deflection value must be within a limit. When a lateral load is applied on the structure, like a seismic load, floor diaphragm forms a load path and provides significant in-plane stiffness for lateral movement. Concrete slab has higher in-plane moment of inertia. If we don't model or consider this in-plane stiffness during structural analysis, we are not replicating the actual behavior of the structure. Not only that, additional story shear is generated due to torsion at the floor level, which can change the rebar demand of peripheral column. To consider all these effects and proper response of the structure during external load application, it is very important to define the floor slab in the analysis model. There are different ways to consider the slab stiffness in STAAD. Concrete diaphragm can be considered as flexible with out-of-plane deformation. To consider the exact response of a flexible diaphragm, we need to model it in STAAD with plate mesh. This is an accurate method as we are modeling the slab geometry properly with opening and connectivity with other element. For complex slab geometry or advanced slab system like a flat slab or PT slab, this is the correct way to model the slab. After analysis, we can utilize the plate stress for design. One major disadvantage: modeling a plate mesh is quite challenging. We must generate it correctly considering all boundary condition and connectivity. Also, it increases the analysis time and model size. Diaphragm can also be defined as rigid, with infinite in-plane stiffness and negligible membrane deformation. For any thick concrete slab with very small membrane deformation due to lateral load, rigid diaphragm is a suitable choice. This method is suggested in different code like ASC 7 with some prerequisite and limitation. In this method, we don't need to model the diaphragm using plate mesh. Stiffness of the slab is defined either using control-dependent relation or using a feature called floor diaphragm. This method eliminates complex plate modeling, hence it is faster. Structural model is light with lesser analysis time. We can perform additional checks like calculation of inherent and accidental torsion due to different center of mass and center of rigidity, perform irregularity checks during seismic analysis. Only disadvantage is we cannot use this method for complex slab geometry with opening or to design it as a PT or flat slab. There are few ways. I'll cover this later. Finally, we can define it as a semi-rigid diaphragm which simulate actual in-plane stiffness and behavior of slab. In this method, we need to model the diaphragm properly with plate mesh like flexible diaphragm. So similar type of advantage and disadvantage. Rather than completely ignoring a slab in the structural model, we can define it using any of these three methods. We can finalize the modeling method based on the project requirement and type of slab like RCC slab or flat and PT slab. For any concrete building with fairly regular slab geometry and opening, it is better to define the slab as rigid diaphragm and avoid modeling it with plate mesh. We can model the beam, column, wall and other load-bearing element. Calculate total dead load like self-weight of slab and floor finish. Apply that as floor load. Same for live load, which we can apply as a floor load with proper load intensity. To consider the in-plane rigidity of slab, we can define each floor as a floor diaphragm. This floor diaphragm option is available in STAAD under specification. Inputs are simple. By default, it is considered as rigid. We only need to specify the floor level and nodes present in that floor to define the geometry. During analysis, program internally calculates the location of center of mass of the floor, create a control node at that location, and considers all other nodes at that floor as dependent node. Program also calculates the location of center of rigidity of the floor. If these two are different, during static seismic or dynamic analysis with TOR command, inherent and accidental torsional moments are calculated and added with respective storage here. If we define a slab with float diaphragm and skip modeling it with FEM, we can export any floor level to RCDC module, then design the slab using an approximate coefficient method based on applied gravity load only. Lateral load is not considered for design, but its effect is already considered during analysis. Another approach is to export the slab geometry to advanced slab design module. Here we can generate a plate mesh, perform finite element analysis, and based on the plate stress, design the slab. This is more accurate than the previous one. Consider this concrete building with irregular floor plan. We want to design this as a hybrid or post-tension slab. For this model, rather than floor diaphragm approach, we can model it with plate mesh and use FEA results for design. But modeling the plate mesh at floor level is a bit tricky. We have already modeled a couple of shear walls with plate. During floor mesh generation, we need to consider all these wall nodes along with all internal beam and column. Instead, there are different mesh generation approach. We can model single plate element, use infill plate or generate mesh option. If we use any of this basic method, beam or plate-to-plate connectivity will not be maintained properly. We need to rectify all those problems manually, which is tough. Alternatively, we can use this parametric model option, which generates a proper plate mesh, maintaining all connectivity. We can select the boundary nodes, where slab profile change one by one. No need to select any internal node. Then provide some basic information like name or type, element type, and size. During mesh generation, program considers all internal element and create the boundary nodes properly considering existing plate or member. As you can notice, all member, node, shear wall plates are considered in this mesh. There is no plate or beam connectivity problem. We can further customize the mesh size, make it coarser or finer, add opening for stair or lift, then finalize this mesh. Using this method, we can model an accurate geometry of the slab with correct boundary profile and opening. After analysis, we can reutilize the analysis result for slab design. For that, we can use an integrated module, Advanced Slab Design or RAM Concept. RAM Concept is a specialized application for elevated slab design. It is a standalone product. We can create any floor geometry from scratch by defining the boundary and other structural element like beam, column or wall, generate mesh, define load, design strips or tendon layout for design. Also, it is integrated with other structural analysis product, STAAD.Pro and RAM structural system. Integration means data exchange. Interface is same. If we model a concrete structure in any of the software, we can export required floor data to Concept and proceed for design. RAM Concept can import floor data along with load directly from STAAD using advanced lab design option. Also, we can use a GCFF file created from STAAD. Apart from this, we can export any floor plan from STAAD as a 2D DXF file and import that in RAM Concept. There are few other approaches using which we can not only import data from STAAD but also from any application including Open Building Designer, Revit, even from an Excel file. How we can transfer the floor geometry to RAM Concept, that I'll cover later. In summary, to design a slab in STAAD, we can either model it as a rigid floor diaphragm where no plate mesh is required, or we can model it as a semi-rigid or flexible diaphragm using plate mesh. Selection of modeling method depends on the slab geometry, complexity and type of slab. We can use Advanced Concrete Design or RCDC module to design a simple RCC slab using moment coefficient method. For complex slab, flat or PT slab, use Advanced Slab Design module. Select any of the 4 methods to export a floor to RAM Concept, then design based on FEA results. That's all about modeling and design of a floor diaphragm in STAAD. Thanks for joining.